Yeah, today's class will be given by Catalina Albornoz. Sorry, I don't know how to pronounce your name correctly. Yeah,
That's
but
good. That's good.
yeah. And then yeah, she is from Xanadu, and then she will basically give an overview about the Xanadu and also the a specific tool set called as PennyLane. And let's welcome our guest speaker.
Yes, thank you. Thank you very much for the introduction. It's a pleasure for me to be here with you. Um, Again, for the last people who joined, the goal here is that you ask all of your questions. We'll first go through a more theory part of things, kind of helping you understand everything that we're going to cover then in the interactive section. So for the interactive part, hopefully you have installed PennyLane in your computer. If you haven't, there's no problem. We can open a Google Colab and then you can install it there. So the goal is that at the end of the session, you will get an idea of what is differentiable programming, what is PennyLane, and what is Xanadu. But mostly, you will hopefully be motivated to learn more of quantum computing and to put it in practice with quantum programming. So without further ado, let me begin. So I am an engineer. I studied mechanical and electronics engineering. I was focusing on control systems, did a master's in France and one in Colombia, where I'm from. Worked in different areas. So during my studies, I didn't get the chance that you have right now of learning about quantum computing. I learned that later on. I worked at IBM. There I became an IBM quantum ambassador. And now I work at Xanadu, which is a photonic quantum computing company. And I work as quantum community manager. So I get the chance to talk to people all over the world and learn how they use PennyLane and also show them all of the amazing tools that we have that are useful for research, for applications, for learning, and more. So the four topics that I will cover today is what is PennyLane, what is Xanadu, how do you do differentiable quantum programming with PennyLane, and how you can take full advantage of PennyLane. So the first question is, okay, I've mentioned PennyLane a bunch of times. PennyLane is the same name as a Beatles song. If you have listened to the music by the Beatles, that's the inspiration for the name of the software, right? So it's a library. Here in the picture, you can see part of the team that works on PennyLane. And this is an open source Python library, which means that the code is available. It's available for you to use to build new code based on this. As long as you cite it, you can use it. You can even do applications on it and charge for them, right? It's open source and it's on Python, which is useful because Python is easy to learn, easy to use. And this library is designed for differentiable programming of quantum computers. So what this means is being able to find the gradients of the circuits in your quantum computers, and then that allows you to do training. So if any of you are maybe have heard of machine learning or classical optimization, the concept of gradients, of differentiability is very, very important. And for quantum computers, this requires special care. So PennyLane is built with that differentiable programming at the core of what we do. And this makes it very useful for areas such as quantum machine learning, quantum chemistry, optimization, and so on. So there are specific areas where you will need to train quantum circuits, and the fact of being able to find gradients or do differentiable programming is very useful. So PennyLane is a library in the end, right? It allows you to integrate quantum computers with classical computing frameworks as well. So you can build modular algorithms that are more powerful than any of the individual components. You can plug and play different pieces together, even run on different quantum computers, and then build like an algorithm that is very powerful and that is modular. You can put those pieces together like a Lego. So this is in one very long and complicated sentence, but this is PennyLane, right? Yet it's more than that. PennyLane is not only some code on a GitHub repository. PennyLane is a community. PennyLane is educational material that we have on our website, PennyLane.ai. PennyLane is a place to meet. PennyLane is events that we make all the time. So PennyLane is more than just a GitHub repository with some code. We have a huge ecosystem, a lot of material, a lot of effort, a lot of people working around PennyLane in making the documentation useful for you, in making tutorials that are useful, easy for you to learn, making interactive exercises and learning platforms. We have a lot of stuff, for instance, events and so on, or even the talk that I'm giving today, that is PennyLane. It's a whole ecosystem that brings quantum computing, quantum programming close to people in a fun, in an easy, in a cool way. Now, the company that I work for, we're the main developers of PennyLane. So PennyLane is open source. It means it's on GitHub. It's free, but Xanadu hires a lot of people to help develop PennyLane. Our hardware, our main core, we're a photonic quantum computing company. So our main core is building hardware for quantum computing. We'll build computers using light. So here in the picture, you can see a chip, a photonic quantum computing chip. And what you see on the right and left is fiber optics. So it's similar to the fiber optic that maybe takes internet to the university or to your home. This allows for really fast communication, and for us, light is quantum. You probably have seen it in the course, or you will see it later on, that light has quantum properties, and so we can use that in our circuits. Unfortunately, light can keep its quantum properties at room temperature, which is a huge advantage. So here in the picture, you can see an example of a chip. Not all of them look like this. This is one example. You have light coming in from the left-hand side through these fiber optics. That light then gets pushed into the chip and then out of the chip into the next one. So now usually we wouldn't leave this gap. This gap is for the picture, but usually this would be like very close together so that the light doesn't escape, right? We don't want the light to escape. We want it all to go through the chip. Our mission, and this is at the core of everything that we do at Xanadu, is building quantum computers that are useful and available to people everywhere. And this is where PennyLane comes in. In order for our quantum computers to be used and available, we need software that is very powerful, that allows us to do quantum algorithms that are able to solve applications and that are usable for people. So this is why we have built PennyLane, to be able to use the quantum computers that we're in the process of building. So we are in the process of building our fault-tolerant modules for our quantum computers that will be released in the future. But in parallel, we have developed PennyLane, and we keep developing PennyLane to be able to deliver the best performance and for it to be the best tool for running quantum algorithms on quantum computers and simulators as well. So in terms of the advantages of photonic quantum computing, well, first of all, there are many different technologies for doing quantum computers. One of them is photonics, and it has specific advantages related to scaling. You may have heard a lot about, hopefully you have heard or will hear about quantum computers having errors today. We will need a lot of qubits in the future in order to be able to have useful quantum computers for application. And in order to have these very big quantum computers, it's useful to be able to make them modular, to be able to network some modules with others, right? To be able to grow your quantum computer. Think of it like having a computer where you can, if you need more capacity of your computer, you can just attach another module and that will increase the capacity, right? Like when in HPC centers, you add more nodes, that will add more capacity. This is what we have in mind. Making it modular and be able to connect some the modules together allows for expanded capacity. It's also easy to scale in terms of manufacturing because we use different processes in silicon. Silicon is a very well understood technology, right? A lot of our chips in the world are made on silicon. So these are technologies that are very mature and they can allow for scaling. And finally, error correction flexibility. Errors are a huge limitation to quantum computers today. And the architecture that we have for photonic quantum computers, for the quantum computers that we are building for the future, they will have the ability to have error correction from the design itself. So this is something very, very powerful. If you combine everything together, then you get Xanadu is a full stack company, right? So the stack is the different layers of abstraction. We have everything from the design of the quantum computers all the way to the packaging. We don't fabricate the chips in-house, but we design them and we test them and we package them together to make the full quantum computer. And in order to be able to use all of this hardware, we built different softwares. So one of them is PennyLane. We have others for different applications. For instance, we have one for quantum error correction. We have a different software, but PennyLane is our largest and our main software product. And this allows you to go from the theory or the algorithms or the hardware all the way into applications. So we also have teams looking into applications, and the main application that we're looking into is simulating batteries. So for new generations of batteries, I guess you have heard how electric vehicles are being very important and batteries can be useful for different energy applications. Being able to simulate and to create better and new batteries that can extract more power from them, that is a very interesting question, and we are studying quantum algorithms for that together with different industrial partners. So this is the main area of application that we're researching. Now, before we go into the next topic, I want to hear questions from you. I've talked a lot about different things, so I want to hear questions. This is the moment. Ask your questions in the chat. Ask about the hardware. Ask about Xanadu. Ask about PennyLane. This is the moment. Come on, don't be shy.
I actually also have a question. The way you generally implement the photonic device, photonic based quantum computing, you actually use the in your company currently you are using the measurement-based quantum computing, or
Yes.
okay. So and then sometimes yeah it was yeah it was a little bit confusing because was that your company or the other company? Yeah, they were also using the Gaussian boson sampling problem, which is a little bit different from which is different from the measurement-based quantum computing. So which one
Yes,
is
that's right. It is confusing. Before we were focusing on Gaussian boson sampling, because this is a problem that is very well suited for photonic quantum computing, which is something that we know how to do. And it's also a problem that is very hard for classical computers to do. So we were focusing on that, and we actually created a quantum computer called Borealis, which was able to achieve quantum computational advantage. It means that it beat all of classical computers by a lot, right? However, we couldn't find any useful applications of Gaussian boson sampling. So Gaussian boson sampling is a problem that we know how to solve. We just don't know what it's useful for, right? And so after research, we couldn't find any useful application, and we moved towards measurement-based quantum computing, right?
okay?
It is important to know that a lot of the development that we have put into the Gaussian boson sampling was very useful for measurement-based quantum computing, right? A lot of the technology, I mean, all of the learnings still work, right? But the exact, configuration is different. So that's a great question. We have both. We are in the process of building our measurement-based quantum computers, and we already have Gaussian, like computers capable of Gaussian boson sampling.
Okay, yeah, thanks. It looks like there are a few questions. Maybe you
Yes.
can check.
What technology is used to fabricate the quantum chip you showed? How many qubits go inside the optical fiber that you showed? Good question. For the fabrication, it's very, so I'm going to say very precise processes that certain foundries can do for creating waveguides in those silicon chips. So it's similar. It's a similar process to what you would use maybe for different kinds of chips in silicon. However, you need a very high level of precision. So there are certain foundries that are capable of doing the exact processes to make the waveguides, to make the light go through. So that, I mean, I don't know the exact, like how they make the waveguides, I'm not sure, but basically that's it. They make waveguides in these silicon chips or silicon nitride chips. How many qubits go inside the optical fiber you showed? You can have, in the experiment that I mentioned that achieved quantum computational advantage, you could have up to 288, but this is not a hard limit. You can technically have more. The problem is that if you have too many, in this case it's Q modes, not qubits. It's like a different version of a qubit. If you have too many of them, at the end you're gonna have like different problems with the phase, with them decaying. So the quality of those qubits will deteriorate after some point. It's not a hard limit, because what we use is that we don't use single photons. That's a common misunderstanding. We don't use a single photon, we use beams of light that go into that fiber optics. So lasers, we use lasers to generate that light, and we use beams of light that go into that fiber optics. So you can put as many beams of light as you want into that fiber, but at some point, if you put a beam of light first and you put 500 beams of light after that, by the time you put in the 500th beam of light, maybe the first one will have decayed and would have lost its property. So it's a complicated question to ask, but at least 288, it worked fine. for the experiment that we published. For the experiment, it was 216, but the device was capable of 288. The second question was, you mentioned about error correction, so I'd like to ask about quantum error correction in photonic quantum computing. How does the photonic quantum computer provide the error correction? Unlike superconducting or iron trap, the photonic quantum computers suffer from qubit loss. Then how do they handle errors, including qubit loss? It's not exactly qubit loss. You maybe are thinking of losing photons, and that happens, but we don't work with single photons. So because we use with pulses of light with many photons, we're not actually losing any, like a qubit itself. The way the architecture works, and actually let me go back one slide for that. We have cluster states. So we create these cluster states with a lot of, in this case, GKP qubits. This is how our, like the architecture that we're building works with GKP qubits. And by combining them together into a cluster state, then you can do error correction. This is how this works. Are quantum hardware from Xanadu available for students through PennyLane? If so, how many qubits are supported? We have one device which is available, which is called the X8 device. It has 8 Q modes. However, it works very differently from what you might be used to. The gates that are used for this device are photonic gates. They're beam splitter and displacement. They're different gates. So you don't, I wouldn't I wouldn't recommend that. I mean, it's a whole different area to learn, basically. If you really want to go deep into learning about photonics, then you should try it out. You should definitely explore it. But if you want to use gate-based quantum computing, and in the end, like the quantum computers that we're in the process of building will be gate-based, so it would be learning something that is not our current line of development. Our current line of development is measurement-based quantum computing. It's gate-based, right? We're creating GKP qubits. So if you're looking into like what we're building for the future, I would recommend that you focus on PennyLane. But if you're interested in the photonics itself, then yeah, you can explore it, and it's called the X8, and it's available for free on Xanadu Cloud. So yeah, great questions. This is super motivating, because then we can, I know that you have really understood everything. Now we're going to talk about differentiable programming with PennyLane. You may have seen, I hope, a quantum circuit before, right? You have some initial state, which are some, basically it's just some vectors, and you have some gates, which are some matrices. And these gates sometimes have parameters in them. They can either be fixed, or they can be tunable, or they can be parameters that you can modify after several iterations if you're performing an optimization, right? So everything, all of this is just linear algebra. And at the end, you perform a measurement. So you perform a measurement on a specific qubit and for a specific observable, right? So in this case, we're measuring on the z-axis, qubit 0 and qubit 1 and so on. These horizontal lines, you know them as qubits, but in PennyLane, we call them wires, because we acknowledge that there are different technologies, and for some of them, these are called Q modes, and for some of them qubits, so we just call them wires, but they're qubits. You will also see that when you have algorithms, you often have variational algorithms. These are very common, very used. You first start with an ansatz, so it's basically like a template for your circuit, how it's going to look. You don't know the exact value of the parameters inside it, but it's more or less the shape of your circuit. You then, this is how we denote like an expectation value. And this is just a function. of your data. So X, we make a difference between X, which is data that is fixed, and theta, which is a parameter that we can iterate over. We can classically join different circuits together and calculate a classical cost function, right? We can say, I want to, these circuits represent some cost. Let's say, for instance, the cost of materials, and I want to eventually build a training procedure to minimize the cost of those materials. Now, this cost doesn't have to be a financial cost, right? It's basically just a classical function that in the end we will want to optimize. And this is important because this will force us to, or allow us to choose a new value for the parameters that go inside our circuit and create a variation every time. So this is why these are variational circuits. Every time we'll create a variation of the circuit with a different set of parameters that will give us a different measurement and that will give us a different cost. And the goal is to get to a point where I can no longer improve those parameters. I can no longer improve that cost. I've got to the best cost possible. Usually it's a minimization. And in order to do that, in order to be able to go from a specific cost to the new value of the parameters, we usually need to find the gradients, right? So in classical computing, we're used to finding gradients. Sometimes we don't even realize it, but we are doing differentiation. When we perform optimization, we often use gradient-based methods. There are other methods, but we often perform gradient-based methods in order to be able to calculate the new value of our parameters. However, on quantum computers, this doesn't exactly work because these are not ones and zeros. This is a little bit more complex than that. So you have other tools, such as the parameter shift rule, where you can find the gradient of a function, basically the gradient of your circuit, which will then you can use to find the new parameters. You can find it by running your circuit twice with different sets of parameters. So we run your circuit twice, and then you subtract the value of that function, and then that gives you the gradient in an analytical way. That is very powerful. That is very powerful. And it means that we can actually, in fact, train circuits and train our quantum computers in a similar way that we would do with classical computers. This is an example, and this is as hard as it will get. This is an example of a gate, so polyrotation gates. Their function, so basically the output of the circuit with polyrotation gates, if you add and subtract an S, a shift, this can be a big shift, so it may look similar to finite difference, but it's not. This doesn't have to be a small shift, it can be a big shift. And then you multiply by a constant and you get the gradient of those polyrotation gates. So if you don't totally get this, that's completely okay. It takes a while to get used to the concept. But the important thing here is that differentiation is important in order to perform optimization. And the way we perform differentiation in quantum computers is different from the way we do it in classical computers. So you can do something like find a difference in both of them, but this is an approximate method. It's not analytical. You can do parameter shifts in quantum computers. It is very slow though. And there are other methods such as backpropagation that you can use on classical computers, but not on quantum computers. So if you are working on simulators, you can use tools such as backpropagation. But if you're actually want to use this on a quantum computer, it doesn't work. So just so that you're aware, because of the way that quantum computers work, the classical methods for optimization and finding gradients don't really work. Oh, I see that there's a question. What is the form of the function f here? The function f, let me go back a second. The function f is basically something that represents how the output, the measurement for your circuit, is a function. It's something that depends on your data and your parameters, right? So it's basically a representation of your quantum circuit. If you think of your circuit like a black box, it's a function. Like the output of your circuit is a function of your data and your parameters. If you ignore the x, if you assume that you don't have any text data and they're all parameters, then this is how you get this f of theta. So this specific f will look different for every circuit, for every gate, for everything. The f will look different. But in PennyLane we have, this is coded within PennyLane, and you don't actually have to worry about how f looks and so on. You don't have to worry about programming this. This is programmed in PennyLane at the core. So that's really good that you don't have to worry about these things. They're already there for you to use, and most of the time you don't even have to think about them. So something that you do need to think about is the fact that you have quantum nodes. So we package everything that is quantum into this green box. Here you have your initial state, your gates, everything that is quantum. And it becomes kind of like a black box for the rest of the program. So you only have to input data. This is classical, right? You input some classical data, some classical parameters, and then you output. You have a function that is an output, and this is a classical value because this is your measurement. This is the result of your measurement. Now, in order to take full advantage of PennyLane, let's think about what we want in a software for programming quantum computers. First, we want to run it on different kinds of hardware. It makes sense, right? We can use PennyLane to run on Xanadu photonic quantum computers, but probably most useful for you. You will be able to run on IBM quantum computers. You will be able to run on other quantum computers with different architectures, and also on simulators. And we also have our own PennyLane simulators, which work really well. So I encourage you to first start with the simulators. You can also interface, and these classical SDKs, we call them interfaces. You can also interface with all of these different libraries, which hopefully you have used or will use at some point in the future. You can also be part of the PennyLane community. So we have big partnerships as well with industrial partners, AWS, NVIDIA, Volkswagen, and so on. And we have events that happen throughout the year. So our largest event, for instance, is called QHack. It happens in February. So if you learn PennyLane really well this year, you can participate in QHack in February. And we have other events that happen along the year. Now we're ready to use PennyLane. So if you want to use it on your own computer, you can pip install PennyLane. If not, you can use a Google Colab. And today, what we will do is something similar to what you see on the screen. So we will program it. I will program it with you, so you don't worry about copying this. We're gonna first import some libraries, right? PennyLane and NumPy. NumPy is for a numerics library. We are then going to create a device, which is our backend. It's in this case, the simulator, or it could be the hardware where we run. We then create a quantum node called Q node, which is our quantum circuit. It has our gates, it receives some parameters, and we output a measurement, an expectation value. And after that, And after that, we will create some classical cross function. That's where we will stop today. If we get some time, we can do other exercises as well. So let me now go to let me go to a notebook. Well, first, if you are using Google Colab, I'm not sure if you are seeing all of my screen. Let me see what you're seeing. Yeah, I think you're seeing. Yeah. If you are using Google Colab, you need to pip install PennyLane. So this is colab.research.google.com. You can just do Shift Enter, and this will install PennyLane in a new notebook. And then you can follow everything else that I'm doing. If you are using a notebook, here. If you are using a notebook, then open a Jupyter notebook. So write Jupyter notebook in your terminal and come with me here. If you're ready, please, or if you're ready or not ready, please tell me know in the chat. Let me know in the chat if you're ready. Or actually, you can also lift your hands if you want. You can lift your hand here when you're ready. Lift your hand when you're ready. I want to see the hands lifted to know.
Yeah. In principle, yeah, we announced that all the students should have PennyLane already installed with the
yeah. And Jupyter as well.
Or Colab. Yeah, but let's see. Yeah, many students are raising their hand. Yeah.
They're raising their hands. So for the students who haven't raised their hands, I'll wait a few more seconds so that you can open your Jupyter notebook. It will be empty, right? You will have an empty Jupyter notebook. That's normal. Just keep your hands up for those who have lifted them up, and for those who are ready, lift your hand when you are ready. So I see a lot of people haven't lifted their hand. If you can let me know in the chat if I should wait more. Somebody is just like getting the Jupyter notebook started. Let me know. If not, I think maybe, okay. I think we might be ready, I guess. So let me begin with Jupyter notebooks. Yeah, let's begin. So everybody can lower your hands. Sorry?
Yeah, some students probably cannot find the button for the raising the hands, depending on the
that's possible.
Interface. Yeah.
Okay, perfect. No problem. All right, so the first thing we will do is we will import. So in the first empty box, right? I mean, probably what you will see, when you open a new Jupyter notebook, you see something like this, right? Just some empty boxes. But I have added some information here to guide you, to make it easier for you. So the first thing that we will do is we will build, so like our first basic example, we will build a circuit with 2 entangled qubits. And then their second example, we will build, the circuit that I was mentioning before. So first we will import PennyLane as QML. Why QML? Because we traditionally, started as a very strong library for quantum machine learning. We're still very strong in that, but now we're also very strong in very different areas, such as quantum chemistry and quantum optimization and other areas, right? So we keep this for historical purposes, import PennyLane as QML. You will also import from PennyLane, import NumPy as NP. So NumPy is our numerics library. Now we will create a device with 2 qubits. So we will write dev equals qml.device. The device that we will use is a simulator. So default.qubits, comma. So default.qubit within, as text, as a string. And we will say wires equals 2. So here from the device, using the device function in PennyLane, we're choosing our default qubit device with 2 wires, so 2 qubits. And we hit Shift Enter, it works. Okay, now we are going to create a quantum node with 2 entangled qubits. So the way we create Q nodes is we use a decorator. So we use @qml.qnode, and then we open parentheses, and we put dev inside of the parentheses, right? So basically, we're deciding we're going to create a quantum node, a quantum circuit, which is going to run on this specific device, which in this case is a simulator. Now, this line has to be on top of a Python function. So we will write dev circuit. It can be called anything. It can be called my circuit, circuit 1, circuit 2, whatever we want. The important thing is that this is right underneath the definition of our Q node. So def of circuits, this takes no parameters. And then we will start adding our gates. So qml.hadamard, and we will apply this Hadamard on the first qubit. So wires equals 0. So note how here, when we define the device, we say the amount of qubits, these are 2 qubits, but the index of the qubits is 0. So the first qubit is wire 0. So they are 0 indexed, but the amount, the quantity is 2. So next we're going to use a CNOT gate. So qml.cnot, and we say wires equals, and then we have square brackets to say 0, 1. So the first wire here is going to be the control, and the second one is going to be the target. And finally, we will finish our Q node with a measurement, right? So return, the return value for this function is going to be our measurement. We will use qml.expval, expectation value. And we will measure on a specific observable, right? So remember how in the first diagram of a circuit, I mentioned that we would measure on a specific observable. So we will measure the poly Z observable. So qml.polyz on wire 0 in this case. We can measure more than one. Yes.
I have a quick question about that expression. So in that case, you can only return the expectation value of the measurement, not the individual shot-based uh, each
Yeah,
measurement.
we have different kinds of measurements. That is a great question. You have probabilities. You can return probabilities. You can return shots. You can return several different kinds of measurements. Yeah.
And then
Actually,
in
let
that
me
case,
jump.
you should define you should use a little bit different decorator, or you still use the same
The
decorator.
decorator is the same. The
Okay.
decorator is the same. The return statement will be different. So I think you're saying what I'm sharing, yes. So everything else is going to be the same, but here the last line, when you return something, it's no longer going to be exp val. It's going to be either sample or counts or probabilities or states, or there's a lot of stuff. For instance, for quantum information, I know that you're going to learn about quantum information. You may be wanting to return some of these quantum information values. You can return them as your measurement, right? You can even combine different measurements, so you can return more than one measurement. And the thing that will change is here, for instance, you have qml.expval and qml.var. You can also return them as a list. We have several examples here in the documentation of how you can perform these measurements. So the documentation is a great place to learn more about the specifics of what you can do. And in the case of shots, for instance, here, you can define the shots when you define the device. So at the moment of defining the device, after you define the number of qubits, you can also define how many shots you want. So great question. Okay, perfect. So now we can, maybe last thing before we run our circuits, I want to draw my circuit as well. So I will write fig, comma, x equals QML dots draw MPL. So we're going to use our nice MATLAB drawer. There is another one that you can use, but this one for small circuits is the best one. And we are going to draw our circuit, but we also have to pass in the parameters. So our circuit in this case doesn't take any parameters, so I just add these empty parentheses here. And that's it. Shift Enter, and I run this, and I get a beautiful circuit. I could have measured on the other qubit as well. This is just an example, right? Oh, actually, I went ahead of myself. I drew the circuit before. Let me draw the circuit here. All right, beautiful. Now, so I'm gonna just stop here for a second in case somebody needs to look back at some of what we did. If you need to take a screenshot or something, this is the moment. But hopefully everybody was able to follow. And then the last thing we do is we can run our circuit. So this is just writing circuits. It has no parameters, so Shift Enter, and I get, in this case, I get a tensor. Do note that a new version of PennyLane comes out every 2 months or so. So the specific code and the specific details, they will evolve over time, right? So do note that I think they're going to change the way this is returned in some cases. So just be aware of that. Normally, you should have no problems. If you had any problems, we will answer your questions. But just so that you're aware, this may look a little bit different with the future versions of PennyLane. So we have some time for another example. So this time we will create a circuit with 1 qubit. It will be very similar to the one we created before. So dev equals qml.device. Here we can use different simulator as well, or the same one. So we can use, let me try lightning qubits, and we will say wires equals 1. So lightning qubit is a fast simulator built on C++. So we create our new device, and now we're going to create another qnode. So add qml.qnode of that device. Actually, I will call it dev2. So we differentiate it, dev2. And I will define circuit 2. And it will take parameters X and Y. And I will create 2 gates in this case, rotation gates, qml.rx, so an X rotation gate. This takes an angle, let's say X, and it will be applied on wire 0, which is the only wire we have, right? We have one single wire, one single qubit, which is 0 indexed. So it's wire 0. Similarly, I will create a Y rotation. So I will add the other parameter. This is going to be an angle because this is a rotation. This takes an angle, which is, one of these parameters. And I will say this is also applied on the only qubit I have, which is wire 0. And let us return or measure. In this case, also the expectation value. It's just a very practical value to calculate, but again, you could use something else. And let's also measure on the poly Z axis. It's very common to measure on the poly Z. Awesome. So what is different this time? We have parameters. This time we have parameters, so this is something that is different. We also have a different device, but it's also a simulator, just a different simulator. Let us draw our circuit. So fig, x equals qml.draw MPL of circuit 2. And this time we will need some parameters here. So let's say, just randomly, I'm choosing 2 numbers, 0.1 and 0.2 for my angles. And let's see. All right. I could add some more details here if I actually wanted to show the values that I'm using. I could add some more details here. For now, we don't need to worry too much about that. Now, if I want to run my circuit, I'm going to say circuit 2 of, let's say, 0.1 and 0.2, and I will get an answer. So far, so good, right? Maybe let me stop for a second there. If you have any questions, this is a good moment to ask them. And for Professor Kim, we have 20 more minutes, right? Okay, great.
Yeah.
Perfect. So everybody, ask away, ask your questions, or let me know in the chat if you've been able to follow so far. So if you have been able to follow so far, maybe write a message, or yeah, exactly, a thumbs up, add a reaction so that I know that you have been able to follow. Okay. Okay, I'm getting a couple of thumbs up. That is great. That is great. Awesome. Perfect. If anybody has not been able to follow, put a reaction or a message in the chat so that I can know. Okay. So I think so far we're doing well. Now we will go and do something even more interesting. So now we've created two different circuits, and now we can actually add some optimization in the mix. So let's create a classical cost function. So I will define a cost. This will depend on my parameters, X and Y. I can define my function however I want. So in this case, I will say that my function is going to be, for instance, the absolute value, so np.abs of the value of circuit 2 for x comma y, right? So the absolute value of the circuits minus 1. I could choose something else. I could choose, so in the example that I had in the slides, we had a sine function. I could choose something else as well. But for now, we're choosing, let's say, the absolute value of my circuit minus 1. Now we can choose an optimizer. And so here, maybe you will remember what I mentioned about the gradients. So in PennyLane, we have a lot of built-in optimizers. So if I go to the documentation and I look at the gradients and training section, that's going to be a very useful section for you. You will see that we have a lot of optimizers that come within PennyLane. So today I'm going to use a gradient descent optimizer, but you can go ahead and try out different ones. You can try even some of them which are not gradient based. So that is interesting. That is different. So today we're going to choose opt equals QML dot gradient descent optimizer, right? And it takes a step size, which in this case we're going to choose as 0.5. So I'll give you a couple of seconds to be able to hopefully write this. I know that the spelling can be sometimes hard, but this is gradient descent optimizer. Now we have an optimizer. So we know that we're going to perform an optimization. We're going to try to minimize this cost function, but we have to start somewhere, right? When we perform optimizations, we have to choose an initial point or initial guess for our parameters. So I will say x equals np array. We're going to use numpy. And here I'm going to actually go back for a second, mention how here we imported numpy from PennyLane. So we didn't say import numpy as np. We didn't just use the last section. We imported a special version of numpy. So this special version of numpy that comes in PennyLane allows us to set some parameters as trainable or non-trainable. So I won't just decide that my initial parameters will be 0. I will define them as an numpy array. So say my initial parameter is 0.1, and I will write here requires underscore grad equals true. So basically I said this parameter is something that I will want to modify. It is trainable, so it requires grad equals true. similarly for y equals mp.array of, let's say, 0.1, requires rad equals true. This means I have set both of my parameters as trainable. My initial guess is 0.1, and I have set them both as trainable. And now I can actually perform the optimization routine. So let's say for iteration I, and I'm going to choose a low number of iterations just to give you an idea of how this works. Let's say we're going to have 10 iterations, 10 steps. I'm first going to define the function to calculate the new updated version of my parameters. So my parameters are equal to, so we're going to use a function called stepped, which is within opt. So opt.step. This will calculate the new version of the parameters, and it will take the name of the cost function, which in this case it's called cost, and it will take the initial version of the parameters, so x and y. So whatever cost takes, so cost takes x and y, which are called here x and y, so I call them here x and y. Now, note how this function, the step function, returns the parameters all together. So I'll need to extract the value for each. So my new x is going to be the first item within params, and my new y is going to be the second item, so item 1 in params. And now I'm going to print. So I'm going to print for each step. I'm going to print the step, and the step is, because this I starts in 0, I'm going to print this I plus 1, because we're used to counting starting in 1, where I'm going to print also the cost. So I'm going to print the cost here, cost of x and y, and I'm going to print x, and I'm going to print y. So this may be a lot. I will copy this for you in the chat. I know that this is, sometimes hard to, get. So this little section, I get that maybe it was a little bit fast, but oh, I haven't run this, sorry. All right, so good. So as you can see, my cost started at about 0, and I'm getting lower and lower until about -1. And similarly, for my parameters, they have started to be modified from 0.1 all the way to about 1.5. And if we went further, we'd probably get closer and closer to -1. So what have we seen so far? Just to go back, we learned how to create circuits in PennyLane. We learned how to create devices, keynotes. We learned how easy it was to, just define a Python function and then add gates to it. This allows for a lot of flexibility. And after you've mastered this, you will be able to use some things such as templates, which will allow you to add information to your circuits in a more easy way. So if you, for instance, want to do algorithms such as QoA, you can use this embedding, or use different templates for performing different circuits. We have learned how to draw our circuits and how to run them. And we have learned how easy it is to change the device that you're running on, right? I just change this little bit when I define the device. And I can use options such as different optimizers that come within PennyLane to create an optimization routine in a couple of lines of code. So hopefully this gave you an idea of how to use PennyLane. In the future, you will be able to perform even more complicated tasks. So in this case, for instance, I show you the results of how you can use a very simple circuit to predict the underlying model in some data. So here we have training data and test data, and we have an optimization result of how I was able to modify the parameters in my circuit to create a quantum machine learning routine and to understand the underlying model in the data. So this is an example of how you can do more complicated things, and not even much more complicated. So to give you a sense, the circuit here is still a 1-qubit circuit. It's just it's a toy problem. It's made right to show as an example. This is to show you an idea of something that you could do. And there's much more. There's much more that you could do. So let me go back to the slides. You can use, for instance, IBM devices. And the example here, you can use IBM on one device and create another device with TensorFlow, and then use a cost function that includes both devices. So function 1 and function 2 combines them together. So you can combine this in a modular way. The templates that I showed before will allow you to create different ansatz, different variational circuits in an automated way. And this is one of the main reasons why this is used so widely in research. So in order to be able to do research, you need to have the flexibility to modify your circuits. And in order to do applications, you need to be able to have the flexibility for this to be useful for your specific application. And so if you do projects afterwards, if you're interested in quantum computing and you want to do projects on this, I encourage you to try out all of the different options that are there that are designed to make it easy for you. You can try other devices as well. So the simulators that are built in PennyLane. So 2 of them we use today, default qubit and lightning qubit. But there's also one for mixed states. So when you have noisy circuits, you would use default mixed. If you're using GPUs, for instance, you would use lightning GPU. And we have another device that has recently been released, which is lightning Cocos for other GPUs. And the 2 that we use today, the default one, and also the one for faster simulations in C++. And so as you saw, as you experimented yourselves, you can combine classical and quantum together. This makes rich, more complex models. So one of the reasons why we want to do this is because we want to expand the possibilities that we have with our classical computers. Often they're not enough. They're not enough to do what we need to do. So we can actually include, hybrid and the quantum parts in our models to make them to be able to find solutions. We're also adding new stuff to PennyLane, I mentioned. One of the latest things is we released a library called Catalyst. So we're in the process of integrating it with PennyLane. This is for just-in-time compilation. So again, we bring the latest research into software. And in terms of the educational material, the first one that I recommend and that hopefully you will get the chance to explore, it's called a codebook, Xanadu, codebook.xanadu.ai. It is an interactive resource where you'll be able to learn about introductory all the way to advanced topics. And you will get to learn the theory and the practice at the same time if you do the coding exercises, like coding challenges that are here in this free learning tool that we have. We also have videos on YouTube. We have tutorials, so PennyLane tutorials, which are designed to get you up to speed, but also advanced research, presentations by different experts in the field. And one of our signature resources are the PennyLane tutorials, PennyLane demos, we call them. They are in PennyLane.ai, and they bring the research closer to you. So if you want to learn about the latest of the latest, or some beginner material, but mostly they're advanced material to learn about different topics in quantum computing in general, right? So we have for specific areas such as quantum chemistry and quantum machine learning, but also quantum computing in general, including, for instance, how different kinds of quantum computers work. So if you want to learn more about how our quantum computers work, you can also find them in our tutorials. And these include text and code, but the code is not executable there. So it's really more like a reading resource. And finally, just to end, welcome you to be part of the PennyLane community. You get the chance to be part of the change, right? This is an exciting time to be in quantum computing. We're building it from the ground up, and you get the chance to be part of that. So you can contribute via code and issues if you go to the GitHub, github.com/PennyLaneAI. You can also ask questions in our discussion forum, both about PennyLane, but also about quantum computing in general, or about, if you want to ask about Xanadu's architecture or something else, you can ask about it in the PennyLane discussion forum. So discuss.PennyLane.ai. And if you want to chat in general with members of the community, you can also go to our Slack. So it's u.strawberryfields.ai/Slack. And if you want to stay up to date with the latest news, you can look for us on Twitter or LinkedIn, or also even subscribe to the Xanadu newsletter at Xanadu.ai. So this is it for today from me. We have, I think, 2 more minutes for questions. So if you want, go ahead with a couple of questions, or let me know what you thought about today. Oh, I see that there is one question. Do you optimize the circuit on a classical computer and then run the optimized parameters on a quantum computer? Or can we run optimization on a quantum computer? Great question, and yes, you're right. The optimization happens in the classical computer, and then the new parameters are run in the new quantum circuit. I don't know of any method that runs the actual optimization in the quantum computer. I don't know of any methods. I don't know for sure that it's impossible, but it's very efficient. Classical computers are very efficient to do these kind of optimizations. But we use hybrid techniques, such as, you eventually will need to find the gradient over the quantum computer by using a classical one. So this is a very good question. What are the pros and cons of QML compared to classical machine learning? Oh, excellent question as well. So there are some bottlenecks, like putting your data, your classical data, into your quantum computer. That is a slow process. It can be complicated, right? That's why you have different embedding techniques. And there's no one answer for all. They will affect how your algorithms perform. An advantage is you can have like higher dimensional spaces, so you can map your problem into a higher dimensional space, which will in some case allow you to find solutions that you wouldn't have found with a classical computer. But for the most part, with the computers and simulators that we have today, for the most part, you get better results with a classical computer. Now, there are specific cases where quantum computers have shown an advantage, but there may be specific cases. Today, like unfortunately, quantum computers are small, and whatever we can simulate on a classical computer is still classical. But there is promise, right? We strongly believe that we can use quantum computers to perform better quantum machine learning, to find better answers to questions that are very hard to get with a classical computer. So this is probably why we have like a very strong research group. We have experts such as Maria Scholl. You may have heard of her. She's one of the leading experts in quantum machine learning. She works at Xanadu, and her team, her group, does very fundamental research on how to find those pros and cons of quantum machine learning. Okay, I guess there aren't any more questions. So let me thank you all for being here. It was a pleasure to be here with you. Thank you for the invitation, Professor Kim. And if you have any questions, Professor Kim has my email, or you can also go to the discussion forum, and also go to PennyLane.ai and check it out. Maybe just I guess I could just show you how to find everything within PennyLane. Maybe that's one last thing I forgot to share. So within PennyLane, you can find all of the resources here in the top. You have like this navigation bar where you can find different learning material, the tutorials, how to install we already installed PennyLane, but you can find more about plugin, the documentation, and so on. For the codebook, you can find it at the bottom over here. So the codebook is a really cool resource. I do encourage you to go and check it out. And for the support, you can go here to the support tab. You can also find the GitHub, but for the discussion forum, you can go to the support tab and you can find the discussion forum where you can create a new topic and that will ask any question. That's it. So again, I hope you enjoyed today, and I'll leave you for now.
I actually also enjoyed your talk today, and then looks like students were more active than I expected. So which is good. And thank you for your time, and then especially you gave all of this tutorial at your 11 p.m. ish. And thank you very much for your efforts. And then I hope that there will be another chance.
Yeah, I mean, I'm happy to be here. I really love being able to share. Like this is an amazing thing that we can do quantum computers from wherever we are, right? Online for free. So I'm happy to share this with you. And now the task is yours to keep exploring the resources and finding new applications and new answers to those questions that you asked. So thank you again, and I hope everybody has a great day today.
Thanks. Bye.
Bye.